Performance guarantees for reinforcement learning algorithms are highly desirable, especially in high-stakes applications such as healthcare or education. But they are also extremely helpful for comparing algorithms and designing improved methods. In this work, we propose a new type of guarantee called Uniform-PAC that helps to better achieve these functions. It forms the missing bridge between the popular PAC and regret frameworks by combining their advantages while avoiding their limitations. In the episodic reinforcement learning setting we consider, regret is defined as follows. In each episode, the algorithm achieves a certain return, shown in green here. We look at the difference between the optimal and achieved return, shown in blue. Regret is defined as a sum of all these differences, and the regret bound is an upper bound that holds with high probability. The other common framework are PAC bounds. Instead of summing the individual differences between the optimal and achieved returns, they are compared to a fixed threshold epsilon. All episodes that are not at least epsilon optimal are considered mistakes, and a PAC bound is an upper bound on the total number that holds with high probability. Both PAC and regret bounds have limitations. PAC bounds do not quantify how bad mistakes are. They do not distinguish between when the threshold epsilon is barely missed and when mistakes are highly suboptimal. Algorithms with PAC bounds also typically stop improving the policy once epsilon optimality is ensured, which means they do not converge to an optimal policy. Regret bounds disallow this, but cannot distinguish between few severe mistakes and many small mistakes. Both frameworks therefore may allow undesirable algorithm behavior. In addition, PAC and regret bounds cannot be compared to each other directly. In our work, we show that regret bounds do not imply finite PAC bounds. Conversely, a PAC bound can, under some limitations, be converted to a regret bound, but that bound is highly suboptimal, which makes comparisons not very meaningful. We therefore propose a new framework called Uniform-PAC bounds. Similar to existing PAC bounds, they bound the number of episodes that are not at least epsilon optimal. But instead of doing so for a single fixed epsilon, Uniform-PAC bounds hold with high probability for all epsilon jointly. Uniform-PAC bounds typically allow only few severe mistakes and more smaller mistakes. That makes them more descriptive than existing bounds, and they therefore imply both strong PAC and regret bounds as well as convergence to optimal performance with high probability. Uniform-PAC bounds help to not only compare methods better, but also design improved algorithms. We demonstrate these benefits by proposing a new algorithm for episodic Markov transition processes with finite-state interaction spaces, and show that it achieves near-optimal uniform-PAC bounds. This work opens up multiple interesting directions. It would, for example, be exciting to see uniform-PAC bounds for infinite horizon MDPs, as well as in general provide a framework for finite sample performance guarantees for algorithms with function approximation. To learn more about this work, please come to our poster with number 198 on Wednesday.